Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about a trapezoidally excited permanent magnet AC motor. So, we saw that the back EMFs in phase A, phase B and phase C are trapezoidal in nature. The rotor has got permanent magnet and we were discussing a two pole rotor structure where we have a north pole and a south pole in the rotor. Let us continue from our previous discussion. So, here we have the phase A, phase B and phase C induced EMF. So, these intervals 60 degree here, 120, 180, 60 is 240, 300, 360 is here and then we have 360 plus 60 is 420 and so on. So, this is the angle theta which is the rotor angle. So, we are plotting this induced EMF against the rotor angle which is theta. Now, this is also known as trapezoidal BLDC motor because the induced EMF are trapezoidal nature here. Now, what should be the current flowing in phase A, phase B and phase C? The current which will be flowing in phase A, phase B and phase C are quasi rectangular in nature. Let us see the waveform of the currents. So, similarly we can plot the current waveforms IA, IB and IC. So, this is for IA. IA is the current which will be flowing in phase A, IB is flowing in phase B, IC is flowing in phase C. So, we have these intervals with us, each interval is 60 degree interval. So, we can plot the current waveforms of this motor, the various current phase current waveforms. So, what about phase A? What should be the nature of phase A current? Phase A current is quasi rectangular in nature which is somewhat like this. This is 120 degree in duration. Now, this is like this, is a quasi rectangular or quasi square. So, this duration is 120 degree and this coincides with phase A constant induced EMF of phase A. When the induced EMF is constant, we have the current, this is also 120 degree. So, the phase A current is positive when the induced EMF is positive, phase A current is negative, here again this is 120 degree. When the phase A induced EMF is negative, this is also 120 degree. And this amplitude, let us say, is E. This amplitude is capital E. This amplitude is capital E here. And the amplitude of the current here is ID. Amplitude of this current is ID. Similarly, for phase B, the current is positive when the induced EMF is positive. So, this is the nature of the current, okay. And the current is negative when the induced EMF is negative. So, this is the nature of the current in phase B. What about phase C? In phase C, we have the current which is like this. The current is negative when the induced EMF is negative and the current is positive when the induced EMF is positive. So, this is the nature of the current in phase C. So, we have the various phase currents IA, IB and IC. So, we saw that the phase currents are quasi square wave and they are positive when the induced EMF is positive, they are negative when the induced EMF is negative. So, how are this current fed to the motor? The motor stator is a 3-phase motor, and we have an inverter, and the inverter is used to feed this quasi square current to the stator winding of the motor. So, we have a 3-phase inverter. So, this is our 3-phase inverter. So, these are the 6 switches of the inverter, and we have the stator phase A, let us say phase B and phase C. So, we have phase A here, phase B here and phase C here, and the inverter input is a DC supply. This is a DC input here, VDC, and this current here is ID, and we have the switch having antiparallel diodes here. The switch is a transistor, we have the antiparallel diodes. This is a VSI structure. So, we have an inverter, and the inverter feeds the stator of the trapezoidally excited permanent magnet AC motor. So, this is phase A, and we have phase C is fed from this point, and phase B is basically from this side, and we are feeding phase B. And this current is IA, the phase current IA. This is IB of the phase B current, and this is IC, the phase C current. And the switch is basically a transistor here. It is equivalent to a transistor. It is a transistor switch. It is a current controlled VSI. So, what we are doing here is a current controlled voltage source inverter, voltage source inverter or VSI. So, we have transistor T1, T2, T3, T4, T5 and T6. Similarly, we have diode D1, D2, D3, D4, D5 and D6. So, this inverter current controlled VSI feeds the stator. This is the stator windings of the BLDC motor. So, the current is regulated as a quasi square wave, and the nature is shown in the diagram here. Now, we will try to analyze or find out the equation for the torque. What should be the equation for the torque? At any given time, we see here that from theta, let us analyze this for theta between 0 to 60 degree. If we take this interval theta from 0 to 60 degree, what happens here? That between 0 to 60, what about IA? IA equal to 0. What about IB? IB is equal to minus of ID. What about IC? IC is equal to plus ID. And what about the induced EMF EA? Is varying. This is varying. What about induced EMF of EB? EB is minus E. What about the induced EMF of phase C? It is plus E. So, for theta 0 to 60 degree, we got the following: IA is equal to 0 and EA is varying. What about IB? IB is minus ID. And what about EB? EB is minus E. What is IC? IC is plus ID. What is EC? EC is plus E. This we can very clearly see here that for the first 60 degree, IA is 0 So, this is what we got here, IA is 0 here, and IB is minus ID, IC is plus ID, and EB is minus E, and EC is plus E. So, for 0 to 60 degree interval, we can find out what is the power into the motor. So, one of the phases is not conducting, that is phase A current is 0. So, when phase A current is 0 and we get this value. So, what is the power here? Power is equal to EAIA plus EBIB plus ECIC, that is the mechanical output PM. So, the mechanical output here, since this quantity is 0, because the current here is 0. So, this does not exist. So, we will say that this is equal to EB is minus E into minus ID plus EC into IC, EC is plus E and IC is plus ID, that is equal to 2 E into ID. So, we saw that the power here is a function of ID, ID is the DC link current, ID in this case is the current in the DC side. So, this current determines this basically function of ID, the power is a function of the DC current, that is ID, which is finally injected into the stator windings. If we want to find out the torque here, torque is the mechanical power by the rotor speed, that is equal to 2. This induced DMF is a function of the speed also. So, we can write down k omega m for E into ID divided by omega m. So, we get the torque as 2 k ID. So, what we saw here is that the torque of the motor is proportional to the current in the windings, that is ID. So, if you want to increase the torque, we increase ID. If you want to decrease the torque, we decrease ID. So, the torque is proportional to ID. So, let us see the plot of the torque in this diagram. So, if we plot the torque waveform here, this is the torque waveform here. The torque is constant, because when ID is constant, the torque will remain constant. So, this is happening for 0 to 60 degree. So, we can also show that for theta varying from 60 to 120, we have a different situation. What about IA, what about IB and what about IC, and we can find out what is EA, EB and EC. So, for 60 to 120, IA is plus ID, IB is minus ID, IC is 0. So, this is plus ID, minus ID and 0. So, this is E is plus E and EB is minus E and EC is varying in nature. So, again for 0 to 60 to 120, we will see that initially we saw from 0 to 60 degree, from 60 to 120 also we will see that the mechanical output is 2 E into ID. So, what about torque? Torque is equal to 2 K into ID. So, torque does not depend upon the interval, it basically depends upon the current. When the current is constant, torque remains constant. So, when we plot the torque waveform here, the torque waveform is a constant waveform. So, the torque absolutely remain constant, it is equal to 2 K into ID. When we change ID, we can change the torque. So, this is a brushless DC motor, but this is a trapezoidal brushless DC motor here, and because the current are quasi rectangular in nature, we can maintain or we can have minimum torque ripple. So, the advantage of this drive is reduced torque ripple. So, the advantage of BLDC trapezoidal BLDC motor, trapezoidal BLDC motor is reduced torque ripple. So, the torque ripple is reduced here. So, this kind of motors can be used for electric vehicle, maybe electric scooters or electric vehicle which are low cost vehicles. So, the trapezoidally excited brushless DC motors are used for electric vehicle because of low torque ripple. Now, this can also be controlled in a closed loop. To control in a closed loop, we have to have a feedback. So, the closed loop control is as follows: closed loop speed control of trapezoidal BLDC motor. So, we start with a reference speed omega m star, and we measure the actual speed, we compare with the actual speed, we feed it to a PI controller, PI 1, this is a speed controller, and then we have a limiter, we have a current limiter here, this is a current limiter. We get the value of the current ID star. This ID star is used as a reference for controlling the inverter. The ID star is compared with the actual ID. We have a feedback of the actual ID from the DC link side, and we go for what is called hysteresis current control. Hysteresis current control, and we control the triggering angle of the inverter. So, this is for phase A, let us say, and depending upon the inverter. So, this is our current controlled VSI, which is feeding the brushless DC motor. Here we have a position sensor, and we have to generate the reference current also. So, the hysteresis current control is fed with the position of the rotor theta, and then we have a speed calculator. So, from the theta, from the position, we can get the speed, that is omega m. And from the current control VSI, we have the DC link here, we apply the DC voltage VDC in this case, and this current is ID. So, we have the current sensor which we can sense from the VSI, and the VSI output is fed to the brushless DC motor, and this is the gate drive generating circuit. Base drive generating circuit, and we give the triggering pulses to the inverter. pulses for inverter. So, this is a closed loop speed control diagram for a trapezoidally excited brushless DC motor. So, when we have a speed error, the speed error gives rise to the reference current. So, we have a reference current here which is obtained from the speed error, and then this is used with a hysteresis current controller. The actual ID is being compared with this, because this decides the torque. So, if you want to increase the torque, we have to increase this ID, and hence this is controlled within a hysteresis band. And then the inverter switches are controlled with a position feedback. So, this is also a self controlled drive. So, we have to have a position feedback for a BLDC motor, which is a trapezoidally excited BLDC motor, and that can be obtained by means of a position sensor. So, this is about the brushless DC motors, which are very popular in vehicle application, electric vehicle application. Now, we will be discussing about another class of motor which are called Swiss reluctance motor. They do not have any rotor windings and they are very lightweight. They can be used for space application. So, we will now discuss the construction and the operating principle of Swiss reluctance motor. This is abbreviated as SRM, Swiss reluctance motor. Now, when we have a coil, say for example, when we have a coil and the coil is carrying a current I and this has the inductance L here. So, the stored energy here is equal to half Li square. Now, if the inductance is a function of the position, we can get a force or a torque. So, if you want to find out a torque here, this is the energy which is E, torque is giving us the derivative of energy with respect to theta at constant current, when current is constant. So, if the energy is derivable with respect to theta at constant current, the derivative of this is the torque. And here, since we keep the current constant, so we have half I square into dl by d theta. So, we are only differentiating the inductance with respect to theta here. So, the torque of a Swiss reluctance motor is proportional to I square and is also proportional to the derivative of the inductance with respect to the rotor position. In this case, to maximize the torque, the current is switched into the stator winding only during positive dl by d theta. If you want to have positive torque, we have to switch the current when dl by d theta is positive. Let us take the constructional principle for a typical Swiss reluctance motor. We take a 8-pole stator and a 4-pole rotor. So, we take a structure and the structure has got 8 stator poles. Or stator teeth, and we have 6 rotor poles or rotor teeth. So, if we take a cross sectional view, the cross sectional view will be of this sort. We have rotor and we have stator. The stator is surrounding the rotor. The rotor has got 6 stator poles, 6 rotor poles. So, this is the structure of the rotor. So, rotor has got the structure which is like this. The rotor has got no windings, but this has got poles like this. So, we have got salient poles on the rotor. So, we have got 6 rotor poles. So, this is one rotor pole, the other rotor pole, the third one, the fourth one, the fifth one here, and we have the sixth one. The stator has got 8 poles here. So, we divide the stator into 8 parts. The stator has got 8 poles. So, we have the stator poles here, and these are the poles of the stator. So, the stator has got windings, and we have got stator poles which are salient structures also, and we have got 8 stator poles. And this is the stator core. So, this is our stator, and this one is the rotor, and we are taking a cross sectional view. So, this is a cross sectional view, and the windings are on the stator. So, the stator has got the windings, the rotor does not have windings. The windings are on the stator, and the rotor has got 6 poles and the stator has got 8 poles. So, by switching the current onto the stator windings, when dl by d theta is positive, because when the rotor rotates there will be inductance variation, and when there is inductance variation we have a dl by d theta. So, when there is a dl by d theta, we have to make sure that the stator current is only present during the positive dl by d theta, by ensuring that the torque can be optimized. So, this is the principle of Swiss reluctance motor. The constructional feature of 8 pole stator and 6 pole rotor we will be discussing more in the next lecture.